Alrighty, so today we're going to wrap up, or at least for this video, we're going to wrap up the divergence test and the integration test for series. Now, all of these series have positive terms. So we're going to do two things. We're going to talk about the p-series in a second, and then we're also going to talk about estimating series with positive terms. So p-series is a series of the form summation n goes from 1 to infinity of 1 over n to the p. Note that p is any real number. So we want to determine the convergence properties of this p-series. Alright, so let's look at a couple of simple cases. If n is equal to 0, then we're looking at the summation n going from 1 to infinity of 1, which I hope you can see diverges, but even if it's not directly obvious that when you add in 1 infinitely many times, it diverges, we can use the divergence test and we see that the limit as n goes to infinity of 1 is 1, which is not 0, so it diverges using the divergence test. If n is equal to 1, we end up with the summation n going from 1 to infinity of 1 over n, and that is just the harmonic series. And we know that diverges because we did that on the last video. Awesome. Alrighty, so now we'll look at two cases. We're going to look at what happens if n is less than 0 or n is negative. And in this case, what happens? Well, first of all, notice that 1 over n to the p, which we can write as n to the minus p, but negative p is greater than 0. So if I take the limit as n goes to infinity of 1 over n to the p, I get positive infinity, which again means that the series diverges by the divergence test. Also logic, but anyway. So let's look at what happens if n is positive. So if n is positive, f of x is going to be 1 over x to the p, which is x to the negative p. And f is, for x greater than or equal to 1, f of x, we could see it's positive and continuous. I guess I'll go in the same order I've been going in all along. So f is continuous. For x greater than or equal to 1, it's positive. I guess I should just keep that later. It's continuous, positive, and decreasing. For x greater than or equal to 1. Awesome. Alright, so we may use the integrating test. That's a new spelling of apply, by the way. Let's try spelling it the normal way. Alright, so we're going to look at the integral from 1 to infinity of f of x dx. So you've got the integral from 1 to infinity of x to the minus p dx, which is the limit. As we usually do, we replace infinity by a parameter b, so we have the limit as b goes to infinity of x to the minus p dx. Taking that little limit, oh man, what is that antiderivative going to be? So we're going to have x to the negative p plus 1, or 1 minus p, divided by 1 minus p. Moving this on to the next page, I'm going to get that the integral of my function is going to be the limit as b goes to infinity of b to the 1 minus p over 1 minus p minus 1 over 1 minus p. So if p is less than 1, right, that means b is being raised to a positive power, and when we take the limit as b goes to infinity, that is going to give us infinity. And if p is less than 1, then we have b becomes to a negative power, so it's in the denominator, and so we get 0. If p is bigger than 1, and we already dealt with p equals 1. So to summarize, we have that my p series, n going from 1 to infinity, 1 over n to the p, converges if p is greater than 1, and diverges if p is less than or equal to 1. Okay, let's box this and see if it's going to work. All right, so that's all you need to remember for the p-series. Excellent. Okay, let's do a couple of examples just to illustrate. Ooh, lots of space there, so if you want to add some extra notes for yourself. Let's determine if the following series converge or diverge. All right, so we have summation n going from 1 to infinity of 1 over n root n. So the first thing I would do is to rewrite this. We can write this as 1 over n to the 3/2. I know you can't actually read my writing, but there we go. That's not even so much better, but we'll try it. And so this is a p-series with p equaling 3/2, which is greater than 1. So we know that the series, what is it? That's right, it converges. Okay. Let's talk about the next example, which is slightly more interesting. So first of all, it's not in the form of, k equals 1 to infinity, 1 over k of the p. Okay. So let's start by just writing down what the first few terms look like. So this gives me, if k is 1, I get 1 over 2 cubed. If k is 2, I get 1 over 3 cubed. If k is 3, I get 1 over 4 cubed, and so on and so on. So we can really write this, if you want to keep the k's, as k going from 2 to infinity, 1 over k cubed. And now we see that this is a p-series. It's a p-series with p equals 3, which is greater than 1. So therefore, I can see that the series converges. Now you may go, wait a minute, that's not the p-series. It didn't start from k equals 1. But the series from k equals 1 would converge, and so if we have less terms, it's definitely going to converge, right? Adding or subtracting a few terms does not change the convergence of the series. So hopefully this all made sense to you. If not, come to office hours or class. I'll create some Zoom sessions for that. In the meantime, let us carry on and look at estimating series with positive terms. So our goal here is to have take a converging series, because otherwise it wouldn't make sense to estimate the remainder. It would be kind of infinite probably. Okay, so what we want to do is we want to estimate our series by a partial sum with the first capital N terms. And so the remainder is the difference between the actual value of the series and our approximation, which obviously would just be the n plus first term plus the n plus second term plus basically the sum of all the terms that we didn't add up. Okay, so if I let S be the infinite series, the value of the infinite series, and this should not say SK. That's called a typo. This should be an S sub capital N being the summation from n going from 1 to capital N. Then the remainder is going to satisfy two inequalities. First of all, we know the remainder is going to be less than or equal to the integral from n to infinity of f of x dx. Now this should make sense to you because when we were looking at the harmonic series as an example, we saw that we were doing is taking the Riemann sum with the left endpoint, and we saw that that gave an overestimate. So it would make sense, potentially, that this is going to be true. And similarly, the remainder, n plus 1 to infinity, let's try that again. The remainder is greater than or equal to the integral from n plus 1 to infinity of f of x dx, because in this case, we're taking the Riemann sum with the right endpoint, which underestimates everything. So we can write this really unpleasant looking inequality. So what you want to think about is that this is the lower bound on the actual sum, which we denoted as s, and this is an upper bound on the actual value of the series. Again, we called that s. And so to get the upper bound, if r sub n is s minus s sub n, you just add s sub n to both sides. And so s sub n plus the lower bound gives us a lower bound on the value of the series. And the s sub n, the capital nth partial sum, plus the upper bound gives us an upper bound on the value of the series. To see this kind of how this would play out, let's look at an example, and we'll consider the series summation n going from 1 to infinity of 1 over n cubed. So first of all, we can see that the remainder is bounded above by the integral from n to infinity of 1 over x cubed, which is 1 over 2n squared. And in case you're like not believing or not sure where that comes from, let's take a quick look. So this integral is, we write this again, use our little parameter, limit as b goes to infinity, integral from capital N to b, x to the minus 3 dx, which gives us the limit as b goes to infinity of negative x to the minus 2 over 2. Fill in the limits. Evaluate at the limits of integration. I get negative 1 over 2b squared plus 1 over 2n. And that limits 1 over 2n. And you know, it would be nice if I squared it. 2n squared. As advertised, I'm actually not sure what just happened there, so sorry about that. Now, suppose we want to estimate the sum to an error of less than or equal to 10 to the minus 3. What do? So this means that we need the remainder, or we need to find n, so that the remainder is less than or equal to 10 to the minus 3. And basically how we're going to do that is that we need 1 over 2n squared less than or equal to 10 to the minus 3. If I multiply both sides by n squared and I divide by 10 to the minus 3, I'm going to get that n squared is greater than or equal to 1/2 times 10 cubed. And per my calculator, I get that n is greater than or equal to 22 point, hold on, I didn't memorize it, 36. So we would choose the nearest integer that's bigger than that, which would be 23. So we would need 23 terms. Next, we want to find upper and lower bounds based on the value of the series. So our upper bound is going to be the nth partial sum plus the integral from n plus 1 to infinity of f of x dx, which is just going to be the summation n going from 1 to capital N of 1 over n cubed plus that integral, which is 1 over 2 times n plus 1 quantity squared. And I encourage you to check that out. You should. Don't just believe me. What do I know? I just work here. And the upper bound is the capital Nth partial sum plus the integral from n to infinity, which we already did calculate, so you can just believe me. So our nth partial sum, we're summing to capital N, 1 over n cubed plus, and then we get the 1 over 2n squared. Okay, so now we've got upper and lower bounds on the value of the series. You might say, big deal. You might, but you shouldn't. So we can use the upper and lower bound to give us an interval for the value of the series, right? Especially useful if we have a series where we don't actually know the value. All right, so we're going to use 10 terms to approximate the series, which tells us that we need the lower bound L10 is going to be summation n going from 1 to 10 of 1 over n cubed plus 1 over 2 times the 10 plus 1 quantity squared. And the upper bound is going to be summation from n going from 1 to 10 of 1 over n cubed plus 1 over 2 times 10 squared. So I guess the first thing I'm going to calculate is the summation from n going from 1 to 10 of 1 over n cubed. So that's 1 plus 1 over 2 cubed plus 1 over 3 cubed plus all the way up to 1 over 10 cubed. And my handy-dandy calculator has told me that that is approximately 1.1975. So, our lower bound then is approximately 1.1975 plus 1 over 2 times 11 squared, which is approximately 1.2016. And our upper bound is approximately 1.1975 plus 1 over 2 times 10 squared, which is approximately 1.2025. Therefore, what this tells us that our series, so the whole thing, the whole shooting match, the sum from 1 to infinity of 1 over n cubed is greater than or equal to 1.2016 and less than or equal to 1.2025. So if you think about it, that was kind of awesome, the fact that we were able to estimate to the hundredths term with very little work. Okay, maybe not very little. Computing some of the first n terms, a reasonably good approximation to our series. We know that series is approximately 1.2. Anyway, suggested problems, and you can see next time we will be working on comparison tests. Awesome. Stay safe, everybody.